All right, so hi everyone. I'm going to slowly start. Welcome back to this series of lectures on disordered systems. Yeah, I'm going to recap what we have done last time. So last time we have started with this Curie-Weiss model, this free energy. Oops, sorry, my technical thing to fix. Since I was starting really early, that's probably not bad. All right, that works now. Yeah, so we had started by discussing the standard Curie-Weiss model and trying to devise an alternative approach to figuring out its limit free energy. Because as I pointed out, in the other two classes of models that we care about, statistical inference and spin glasses, the approach based on large deviations is, as far as I understand, not applicable. So we need to find another approach. And the approach that we are exploring is based on partial differential equations. So we denote Fn, the free energy of the standard Curie-Weiss model. And we observed last time that this free energy satisfies this relationship between derivatives. And so that gives us hope that in the limit of large n, the limit satisfies the same equation with 0 on the right-hand side. And we've seen that it's not completely clear how to make sense of this. We have to find the right notion of solution for this limit. And we introduce the notion of viscosity solution for this purpose. And we've seen that at least, I created examples of spurious solutions, and we have seen that this notion of viscosity solutions allow to rule out these spurious solutions I had built by hand. Okay, and so I have not yet proved that there are unique, that viscosity solutions are unique, but we're going to do that today. And before we do this, I would like to clarify that indeed the free energy converges to a viscosity solution of the equation. So yeah, let me also add that we have observed that this function Fn at time 0 does not depend on n. Okay, and we denote it by psi. And let me add one more remark. So you remember that the way we derived this identity was by observing that the derivative in H is the mean magnetization. And this thing is the average of the square of the mean magnetization. So what I want to point out now is that both quantities are between -1 and 1, because these mean magnetization things are between -1 and 1. And if I square, this remains true. So observe that okay, so because of this, you know that this family of functions Fn is equicontinuous. And also this at time 0, the value is fixed independently of n. So by the Arzelà-Ascoli theorem, you know that there exists subsequential limits, like up to extraction of a subsequence. We can make this series sequence of functions converge for the topology of local uniform convergence. So by Arzelà-Ascoli. This is a pre-compact sequence. Okay. So if we want to identify the limit, we don't have to worry about boundedness. Let's say we just need to worry about about asserting that any possible limiting point along some subsequence is unique, is uniquely identified. And as a first step towards this goal, let me show that any limit along a subsequence must be a viscosity solution. Okay, so each time I speak about convergence of these functions, this Fn, I mean in the sense of local uniform convergence. So let F be any subsequential limit of Fn, then F must be a viscosity solution of the equation. And clearly, the initial condition is also equal to psi because this does not depend on n anyway. All right, so let's prove this. So essentially, we have already done the proof. I'm going to re-say it just to make sure we're all on the same page, but this will be very similar to what we have done yesterday. So yeah, so for convenience, let me not display the subsequence. Okay, we understand there's a subsequence, but I'm not going to write it down explicitly. And so I'm taking a, we remember the definition of viscosity solution. I have to take a smooth function and the contact point. So let th in 0, infinity, cos r, and phi, a smooth function, be such that f minus phi has a strict local minimum I'm going to use max, sorry, at th. Okay, so I discussed in words, I did not write down the proof explicitly, but I discussed briefly that in this definition of viscosity solutions, we can equivalently write local maximum or strict local maximum. So here, for convenience, I'm going to use the version with strict local maximum. Okay, and so Fn, there's along this subsequence, the functions Fn converge to F. So since, okay, but since Fn converges to F, let me ignore the subsequence. There exists this local maximum has some precursor for the functions Fn. So there exists Tn Hn converging to Th such that at least for n sufficiently large, Fn minus phi has a local maximum at Tn Hn. So yeah, so if you want, I wrote this was the third problem in the fourth problem set, and I wrote a solution to this. So if you go to the overleaf document, you will find an explicit argument for this point. Yeah, I think there's someone who is not muted. Maybe I think Omer, I muted you. Sorry. So we already did this argument. Remember that at this local maximum, the derivatives of fn and phi must coincide. So this is very convenient because fn is a smooth function. Okay, so we can really think about the derivatives. The derivatives of fn and phi coincide. I mean, derivative in t and in h. And moreover, the second derivative of fn minus phi has a sign. Okay, so let me dt of fn minus phi at t and hn equals 0, and it's the same with the h derivative. And the second derivative is non-positive. Okay, so we want to understand the behavior of the, like the equation, but computed at the smooth test function. So I want to understand this. Well, technically, I would like to understand at th, but first I do it at t and hn. So this is the same as dt fn minus dh fn squared at t and hn, which is 1 over n dh2 fn at t and hn. Okay, this is by the equation satisfied by fn. And now we use the inequality above, which tells us that this is smaller than or equal to 1 over n dh2 phi at t and hn. Okay, and then we pass to the limit n going to infinity along the subsequence, and we get the result. Okay, so passing to the limit, we get dt phi minus dh phi squared at th is non-positive. So this shows that the function fn, sorry, the limit f is a subsolution to the equation. So how does the first equality hold? Is because these derivatives, they coincide. So this equality here is true because we have these identities here. You see I think that's what I'm talking about. You see that the derivatives of fn and phi are the same at the contact points. Does that make sense? Yeah, another thing I should have stressed is that, so let me point out something interesting, which is in order to indeed justify this point, I need to know that Tn is strictly positive, because otherwise I will only have an inequality. If I only know that fn minus phi has a local maximum, but the maximum is at the boundary, for Tn equals 0, I will not be able to assert that this derivative is 0. I will just be able to assert that it has a sign. But look carefully that here I assume that t is positive, strictly positive, as we would say in French. And since Tn converges to t, for n large enough, Tn is strictly positive as well. Okay. So this derivation here uses that Tn is strictly positive. And this is important. Okay, so it was important for me that in the definition of this solution, I only look at contact points which are detached from 0 for the t variable. Otherwise, there will be a gap in my argument here. Okay, and for the converse argument, for the super solution argument, it's really the same. So I'm not going to do it. Okay, so the same reasoning shows that. F is a super solution. Okay, so that completes the proof. So it's interesting. We have built a new notion of solution to the limit, and at least we can verify that any possible limit point of this free energy we care about must be a viscosity solution. Now, for the meaty part, can we say that there is a unique viscosity solution? Okay, so this is what we're going to discuss right now. Are there questions so far? So I'm going to state something which is in fact a bit stronger than the uniqueness of solutions. And it's really, I already spoke a lot about the maximum principle. So it's going to take the form of a comparison principle. Let me state it and then comment on it. So I'm going to take a subsolution and a super solution. And without loss of generality, I'm going to do it for the general equation, where the nonlinearity is this H guy. And for technical reasons, I'm going to assume that both functions are uniformly Lipschitz continuous in the x variable, like the variable which is not t. Which sometimes I also denote H, actually. That's right, Lipschitz. So the claim is that the supremum of u minus v is achieved at the initial time. So a sub-solution, you should think of this as something which stays below the true solution, and the super solution is something that may go above the true solution. And we're saying that, let's say that at initial time, u is below v, so sup of u minus v is, let's say it's 0. So they are touching, but u is below v. Then this comparison is preserved over time. Uniformly Lipschitz, I mean as opposed to locally Lipschitz. Yeah, I mean, I was worried that if I just write Lipschitz, maybe people would think it's locally Lipschitz. I want one Lipschitz constant for which is valid everywhere. So maybe Lipschitz would actually do as well. Yeah, I use uniformly Lipschitz, but just to make, I try to emphasize, but maybe it's actually not clarifying. Okay, so let's, yeah, exactly, yeah, for all time and uniformly in space. So let's clarify first that this result indeed guarantees that we have unique solutions to the equation. So consequence, say if u and v are two solutions, with the same initial condition, then they are equal. The reason is that Well, if U is a solution, it's in particular a sub-solution. And if V is a solution, it's in particular a super solution. So I can apply the result. And the result tells me that, so indeed, the theorem says that we must have U smaller than V. You see, it says that the supremum of U minus V must be 0. But then you can exchange U and V, and you also have the other inequality. And so by symmetry, we get the result. So there's a question about whether the result is still true if we drop the Ellipses condition. I'm not entirely sure. At least I would be worried if there is absolutely no control in the space variable. So I suppose you can weaken it substantially, but if you write nothing, I would be a little bit worried. At least maybe it's because I'm not. I haven't tried very much because the functions we care about are all uniformly Ellipses. You know, we can always bound the derivatives by 1 for these three energies. But it's not obvious to me how to carry on the proof. So maybe it will be more apparent that it's not obvious as we go along. But okay, maybe people who know more about Hamilton-Jacobi equations would tell me what is the optimal condition. I'm not sure exactly what it is. Yeah, I thought, before I go to the proof, I wanted to make another small comment, which is because of the previous result we have proved, the fact that we have this function fn, and we know it's pre-compact. We know it has subsequences that converge. We really don't need to worry about existence of solutions because this gives us at least one solution, maybe even more. Okay, so really the only thing we have to worry about is their uniqueness of solutions. Okay, so maybe I'm going to first write a very rough idea of how we could try to approach this thing. So this is going to be very rough, okay? But I think it's useful as a first try. Suppose that we have instead, so you remember this, I can use this notation to denote that this is a sub-solution. And I'm going to assume that I can insert a little bit of an epsilon here. And this, we'll see this is possible. This is not where it's the most shaky part of my rough ID thing. So I'm going to assume that U solves this. And recall that V is a super solution, which I'm going to write like this. And now here's the sketchy part. So take Tx such that U minus V is maximal. And if T is not 0, then we must have dt of U minus V equals 0 at this point. And the gradient must be 0 as well. Okay, so the derivatives coincide, but we have said that at Tx, but we have said that this expression in terms of the derivatives is smaller than minus epsilon. This one is larger than 0, so there is a contradiction. Contradiction with the first line. Okay, so this is kind of shaky. First, because I assume that this maximum is achieved. And second, because I pretend that these functions are differentiable, which we know they are not. Okay, so I see another question in the chat. Why is this uniqueness result interesting in terms of the models we want to study? The reason it is interesting is that we want to put our finger on the limit for energy. And at least as a first pass, I'm going to try to talk about the limit as saying, in fact, it's the unique viscosity solution of this equation. Okay, so that's one way to single out a particular function and say, okay, this is the limit of my free energy. And maybe later we will actually realize that this solution also can be expressed using the variational formula that we have discovered using large deviations. But for now, I just want to say, I just want to find a way to identify what it is that it converges to, like to find some sort of self-contained way to talk about it. And one possible self-contained way to talk about this limit is by saying it is the unique viscosity solution of this equation. Okay? And I want to justify that this is a meaningful sentence, that really there is a unique solution. Does that make sense? Okay, so yeah, the big problem, the biggest problem in this very rough idea is that I'm pretending that the solutions are differentiable and they are not. So now I'm going to move to Sketchup proof of the comparison principle, where but essentially it's a rigorous proof, except that I'm not going to deal with the fact that RD is an unbounded space. So I'm going to pretend that RD is the torus, if you want. So pretending that RD is the torus. The d-dimensional torus. Okay, or if you want, I'm going to pretend that RD is compact. Okay. It's not true, but it's kind of, obviously it's going to simplify my argument. And then later I'm going to explain, but perhaps not in full details, how you patch this problem. And in the notes, there is a complete proof of the result on RD. Okay, so we are in this Sketchup proof. I'm allowing myself to pretend that RD is like the d-dimensional torus instead. I'm going to pretend that RD is compact. So I'm going to argue by contradiction. No. So the contradiction is just that you get that these quantities at Tx should be equal, but one is smaller than minus epsilon and the other is non-negative. That's the contradiction. So if the statement is false, then I can find U a subsolution, V a super solution, and a time t, such that the supremum over 0t cross RD of U minus V is strictly larger than the supremum at the initial time. Okay, and I'm going to start by making some modification to this function to make sure that I can find like that the optimizer for the soup on the left side, I would like that it does not touch the endpoint. So I'm going to bend the function downwards near capital T so that I can have an optimizer which is an interior point of my domain. So let's say for epsilon positive denote chi of t to be the following function. So epsilon divided by t minus t. So for epsilon sufficiently small, I can make sure that the supremum, so now I'm going to open the interval, of u minus v minus chi is still strictly larger than the supremum at the initial time. Okay. The reason is just that I can find a t naught not equal to capital T, such that this quantity on the left is larger than the soup at the initial time, and then I optimize epsilon, and this is always possible. Okay, and now the key idea which allows us to get around the difficulty I was pointing to in the sketch, which is that u and v are not differentiable, is to double the variables. So let me write this down. So for every alpha larger than 1, consider the following function: psi alpha of tx t prime x prime, which is u of tx minus v of t prime x prime minus alpha over 2 t prime minus t squared plus x minus x prime minus x squared minus chi of t. Okay, so you see it's very much in line with the idea that we are looking for this point which maximizes u minus v, but instead we allow a little bit of wiggle room, and we don't force the tx and the t prime x prime to be equal. Instead, we have this quadratic penalty, and I'm thinking of alpha as being very large. So t and t prime are going to be extremely close. So it's really essentially as if we're optimizing u minus v, except we allow a little bit of wiggle room, so that if the we can, then we will be allowed, we'll be able to use the definition of viscosity solutions properly. And then this last guy is to make sure that we are not going to touch the endpoint as we do the optimization. Okay, so that's so it's based on the idea that we can only think about optimizing u against a smooth function. So this will be, we're going to think of t prime x prime as being frozen, and then we optimize over tx, and so this will be smooth, and we'll be able to use viscosity solutions for this, and vice versa. Okay. So it allows you to touch u by a smooth function, while if you do the soup over u minus v, v is not smooth. So you do this expansion. Okay, so this I'm going to maybe keep to the break, but it's not too difficult. So for this epsilon, there's a question about the epsilon thing. You just take a t naught such that u minus v of t naught x naught is strictly larger than the soup at the initial time, and then you try to insert epsilon. If you choose epsilon sufficiently small, this will remain true. The u minus v minus chi at t naught x naught will still be greater than the same thing at the initial time. Okay, so we're trying to optimize this psi alpha. So the soup of psi alpha is achieved at some point. T alpha, x alpha, T prime alpha, x prime alpha. Okay, so this is where I use that, I pretend that RD is the torus. So, you know, in principle, if you're on RD, maybe the soup is not achieved because as you go further and further away, you have better and better results. But I'm ignoring this here. Yeah, Connor, if you're still not convinced, we can shortly. I will take a break and we can talk about it more carefully for the epsilon thing. Okay, so I have this T alpha, X alpha, etc. And again, I'm pretending that we are on the torus for the space variable. So up to extraction of a subsequence, I can assume that these points converge as alpha goes to infinity. Okay, so the first thing I want to say, and maybe then we take a short break, is that it must be that T0, T naught is equal to T prime naught, and X naught is equal to X prime naught. And this, okay, you know, this is consistent with the intuition I was trying to convey, that we're adding this penalization term, but when alpha becomes very large, it becomes extremely costly to get any significant distance between T alpha and T alpha prime. So as alpha goes to infinity, these two things will collapse. Okay, and to see that this is true, observe that. So I'm pretending that the space variable lives in the torus. U and V are continuous functions. So the supremum of U minus V, or even the supremum of U minus the supremum of V, or minus the infimum of V, this is bounded. So it has to be that this quantity stays bounded. Otherwise, you would pay too much of a price. So since, let me write this, U and V are continuous. And again, I'm using that we are on the torus in the space variable. We must have that. That this term alpha over 2 T prime alpha minus T alpha square plus X prime alpha minus X alpha squared remains bounded. Okay, so just to say it one more time, if this was to not remain bounded, it would mean that when we optimize psi alpha, this grows towards minus infinity, but this cannot compensate for this growth. You know, this remains bounded. So it's bizarre because we're optimizing psi alpha, but in fact, like, you know, along, if it were the case that this diverges, then we would have that the supremum of psi alpha goes to minus infinity. But this is clearly not the case. I can always set tx equals t prime x prime and find a decent value for the super for the psi alpha. Does that make sense? Or? Okay, so let me write the conclusion and then I take a little pause to make sure that we're all on the same page. So this tells us that it tells us that this thing goes to 0 when alpha goes to infinity, and this thing as well. So T0 must be equal to T0 prime, and X0 must be equal to X0 prime. Okay, so maybe now I take a short break. So yeah, so let's take a quick break. Is it still unclear, the epsilon thing? I suppose. I had the impression that given the okay, so I'm going to assume it's still unclear. Okay, so I'm going to re-explain the few things where I was a bit quick in this derivation. Okay, so first for the epsilon thing. From this, I can have that there exists a T bar, such that U minus V of T bar X bar is larger than the soup at the initial time. Okay, and let's say T bar is below capital T. Okay, this is by continuity. Okay, this exists, right? And then I'm saying that if I choose epsilon small enough, then I will have that U minus V minus chi of T bar X bar is still larger than this thing. Okay, and so that's already sufficient for what I want to show. Does that make sense? Hello?
Yes.
Okay. The person who asked the question does not reply, but okay, so I'm going to erase. Well, okay, I'm leaving it there because I'm worried that. So okay, so now for the boundedness of this quantity, I'm saying that the supremum of psi alpha is going to be larger than some quantity, which does not depend on. So let me write it explicitly. So it's going to be larger than, let's say, U minus V minus chi of 0. Okay. That's kind of clear, no? And this soup of psi alpha is by definition U of T alpha X alpha minus V of T alpha prime X alpha prime minus alpha over 2 T prime alpha minus T alpha squared plus X alpha prime minus X alpha squared minus chi of T alpha. Okay, so this is equal. So if you reorganize this inequality, this is non-negative. Okay? So we don't need to worry about it. And this will work out. Okay. Yeah, because this remains bounded also. This U minus V guy. Okay, and it's a useful discussion because we see also for the same reason we see that the chi alpha will also remain bounded. So we see that T alpha will remain away from capital T. And that was the purpose of the function chi. So notice that chi of T alpha is smaller than some constant, which does not depend on alpha. Okay, so this is it's a very useful point for later. This is exactly what I wanted to have. So even in the limit, T naught will be smaller than capital T. It will be an interior point. Are there other questions? Okay, let me get a bit of water and I'll be back. All right, so let's continue through this proof. So we have doubled these variables. So instead of optimizing u minus v, we're optimizing this u of tx minus v of t prime x prime with this big penalty term, which is forcing the t and the t prime to be very close and the x and the x prime to be very close. And now I want to argue one more thing, which is that so we have just seen that T naught is not going to be the final time. I also want to say that T naught is not going to be the initial time. And this should come from the assumption that the soup of u minus v is achieved not at the initial time. So remember that the whole argument is starting from this point, okay? Here. That this soup over the whole interval is achieved not at time 0. Okay, so I want to use this to observe that T naught is strictly positive. So observe that this is true. Okay, I'm free to, in this optimization of psi alpha, I'm free to choose t equals t prime and x equals x prime if I want. And in this case, the function I'm optimizing is just u minus v minus chi. So in particular, this inequality is true. But I also have that psi alpha of t alpha, x alpha, t prime alpha, x prime alpha is always smaller than u of t alpha, x alpha minus v of t prime alpha, x prime alpha minus chi of t alpha prime. Sorry, t alpha. Okay, because I just removed the penalty term. The left side here, the psi, is the same as the right side, except there's also this minus and then the squares. And now if I pass to the limit, the functions u, v, and chi are continuous. You remember that T alpha converges to something, not the final time. So by continuity, so what I want to say is that this thing goes to u minus v minus chi at t naught x naught. And so by combining the two inequalities, we get that the sup, over 0t course Rd of u minus v minus chi must be smaller than or equal to u minus v minus chi at t naught x naught. Okay. And in fact, you see that this must be an equality, right? Because the left side is an optimization that includes the term on the right side. So this is an equality. So it must be that T naught is strictly positive, right? Because this sup term is strictly larger than the sup at the initial time. Okay, so we must have T naught positive. Does that make sense? Okay, I found that the supremum over the whole interval is actually equal to u minus v minus chi at t naught x naught. And this quantity is strictly larger than the supremum where I restrict to the initial time. So it cannot be that T naught is 0. Okay, and in particular, so we have seen that T naught is strictly positive, not equal to the final time, capital T. And so for every alpha sufficiently large, we also have that these things are also true. For every alpha sufficiently large, we have that the T alpha and the T alpha prime are strictly between 0 and T. Okay, and now that's all I wanted to argue. Now I'm going to, now that I know that my contact point is away from these boundaries, I can apply the definition of viscosity solution. So let's recall that. Notice that the mapping. So we have optimized over these variables tx and t prime x prime. So in particular, if I freeze, let's say the t prime x prime, and I optimize over tx. Okay, so let me write it down because saying it is more difficult than writing it down. So if I consider this mapping, tx minus, I substitute the t prime by the optimal values, minus alpha over 2 t minus t prime alpha squared plus x minus x prime alpha squared minus chi of t. This mapping is maximal at t alpha x alpha. Okay, so we have found, we have a smooth function. That was the point of the doubling of the variables. Let me give it a name. So yes, this thing I'm going to call. So let me organize the parentheses a bit differently. I'm going to bracket it like this. Okay, and this I'm going to call eta of tx. Maybe, yeah, maybe phi would be also a good notation. Okay, so we have, and this thing is a constant. Okay, so I can, if you want, I can put it in the phi or in the definition of phi. We can just ignore it. Okay, if I was not writing it, it would still be true that the mapping I write is maximal at t alpha x alpha. Okay, so let's just ignore this term in the middle. So what we're saying is that u minus this smooth function has a local maximum at t alpha x alpha. And so by the definition of being a subsolution, we infer some information about the derivatives of phi, since u is a subsolution. So dt of this. Okay, let me change notation one more time. I'm going to only include the. We understand that the test function is the sum of these two terms, but I want to give a name just to this guy. So this one I'm going to call, and let's just say phi. Okay, and I'm going to write phi plus chi minus h of grad of phi plus chi is non-positive. Oh, sorry, say at this contact point, t alpha x alpha. Let me write this back. Okay, this is by definition of being a subsolution. And chi does not depend on x, so grad of chi disappears. And so if I rewrite this explicitly, I get dt phi minus h of grad phi at t alpha x alpha. And then I'm going to write explicitly what's this derivative of chi. Chi is epsilon divided by capital T minus t. So if I differentiate, I'll get minus epsilon divided by t minus t alpha squared. Right? Everybody is agreeing with that? And now I'm going to play the same game, but like freezing the t alpha x alpha and optimizing over the t prime x prime variables. Similarly. Yeah, notice that here I use the fact that t alpha is not one of these extreme points. Okay? Otherwise, I will not be able to apply the property. So similarly, if I look at the mapping, so v of t prime x prime minus u, then it's, so I'm putting a minus sign in there, so that we are matching this form of v minus test function has a local minimum. So it's plus alpha over 2 t prime minus t alpha squared plus x prime minus x alpha squared plus chi of t alpha is so has a local minimum at t alpha prime x alpha prime. Okay, and again, so this guy is a constant, we can just ignore it. This guy is a constant, we can just ignore it. And And this guy I'm going to call minus phi tilde of t prime x prime. Okay, so I have that v minus phi tilde has a local minimum at this point. So since v is a super solution, we deduce that dt of phi tilde minus h of grad phi tilde at this point, t alpha prime x alpha prime, is non-negative. Right? And now I claim that there is a contradiction in the two inequalities that are written currently on the slide. Okay, so I claim that there's a contradiction between this one and this one. And the reason is that, so let's remember what phi is. So phi is defined here. So if I look at the t derivative of phi, let's say, it will be alpha t alpha minus t alpha prime, if I compute it at t alpha. Okay, so the t derivative of phi at t alpha is alpha t alpha minus t alpha prime. And it turns out that it's the same as the t derivative of phi prime computed at t alpha prime. So let me write this down. What is that? Partial t phi at t alpha x alpha is equal to partial t phi tilde at t alpha prime x alpha prime. And similarly for the gradients. Okay, this is by symmetry of this function. The fact that we build this function as being symmetric functions of the difference is responsible for this property. And so indeed, we have a contradiction between the two displays, okay? Because these identities tell us that this guy and this guy are equal, but we've said that one is non-negative and one is smaller than this minus epsilon, blah, blah, blah. So we have reached a contradiction, and that's what we wanted to do. Okay, that's the end of the proof, therefore. We have argued by contradiction, and we have succeeded in doing this. So this extra minus da 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 is coming from this chi function that we smuggled in. So in fact, the chi function is serving two purposes. One is to detach these optimization points from the endpoint, and the other is to you know, in my rough sketch. Where is the rough sketch? Oops, it's here. In my rough sketch, I wanted to assume that the subsolution U has an extra minus epsilon here. And in fact, this chi is also giving me a bit of this. Okay, so it's also playing this role if you want. And you know, in practical terms, when we do the argument, the test function we are using for the function U is this whole thing, you know, as a function of t and x. So when I write the relationship with the derivatives, the test function is the sum of phi and chi. Okay, and then I just compute what are these derivatives. So the gradient of chi is just 0. Okay, chi does not depend on x. And the t derivative of chi is that guy. yeah, where do we employ the uniform Lipschitz continuity in the x variable? Nowhere, but I pretended that RD is the torus, which is not true. So the Lipschitz continuity is used to deal with the unboundedness of the domain. So maybe, okay, if there are no further questions, I'm going to expand upon this. So in fact, if you want to, yeah, I'll just wait for just a few seconds to make sure this is okay. So yeah, the thing is that when you when you really do the full proof, the one for RD, you need to make sure that these variables do not go out of the window to infinity. You know, like each time I was optimizing over x or x prime in this Sketchup proof, I pretended that they stay in a compact set, but it's not necessarily the case. So we would like to insert some truncation that prevents this from happening. So a little bit like this chi function gave us some truncation in the t variable that told us that we are not going to optimize at the boundary of the domain. Here I want to introduce a truncation in the x variable, which is going to tell me that my x alpha, x prime alpha are not going to fly off to infinity. And so in fact, it's useful to think that you're going to try to prove, in fact, a stronger version of the comparison principle. So let me write it. So I'm going to state the result that includes this truncation in the x variable. So let me write it down, and hopefully it will clarify itself. I will say some more once it's written down. So let's fix ourselves a final time. Let's U and V be, so it's, U is a subsolution and V is a super solution. And let's say it suffices that there are solutions up to time t. And again, I assume that they are uniformly Lipschitz in X. So I'm going to call the Lipschitz constant L. Okay, it means that if I look at U of tx minus U of ty in absolute value, this is bounded by L times the norm of x minus y for any t. So both uniformly L Lipschitz in the x variable. So I want to define one more quantity. So I'm going to call V. V is going to be the Lipschitz constant of the nonlinearity in the equation. And this is for P prime, for P and P prime, which are at most L. It makes sense that I only look at H for arguments that are at most L, because the gradient of the functions I care about never exceeds L. So what the H does outside of this region should not matter in the equation. It's H of grad U, H of grad V, so only these things will matter. And now the claim is that for every R and M, so for every R and M, such that M is at least twice the Lipschitz constant, the mapping Tx maps to U of Tx minus V of Tx minus M times X plus Vt minus R, positive part, achieves its maximum, or its supremum rather. Well, okay, so it's also a maximum at a point with t equals 0. Okay, that's a long statement, but it's a much more precise statement than the previous one, and it's the one that one should try to prove. In fact, so if I had to give you a full proof of the comparison principle I gave you initially, in fact, this is the statement I would want to prove. Okay, because this is a statement that speaks of what happens with this cutoff in the x variable included. So you see that I chose, in the statement, I chose m to be larger than twice the Lipschitz constant, so that when x goes to infinity, this term is really going to kill u minus v. So if I look at the supremum, it's clear that the supremum will be achieved in some bounded region. If I fix the t, let's say, and I optimize over x, I will not be worried that the optimizer will go to infinity. And so this plus is this plus means the positive part. Okay, it's the value of the object if it's non-negative, and otherwise it's 0. What other comment do I want to say? Yeah, and R is of our choosing. So, okay, so I claim that this statement implies the comparison principle. Maybe I can justify this. Well, I call it stronger form, so let me justify that. Stronger than the previous comparison principle. So indeed, let me try to prove this first comparison principle I stated using this theorem. So indeed, we can prove the true comparison principle, the initial, let's say the weaker comparison principle using this in the following way. So again, we argue by contradiction. So suppose that the supremum of u minus v is larger than the supremum at the initial time. I want to, okay, so I want to find a way to use this strong comparison principle. So let's say that there exists T naught, X naught, such that U minus V of t naught x naught is strictly larger than the soup at the initial time. And then I'm going to use, so m I can choose to be, let's say, 2l plus 1. And I'm just going to fix r to be sufficiently large so that it does not disturb this property. So fix m equals 2l plus 1 and r equals x naught plus v t naught. So that's u minus v. Okay, maybe I can. U of t naught x naught minus v of t naught x naught minus m x naught plus v t naught minus r, positive part, is equal to u minus v at t naught x naught. And this remains larger than the soup at the initial time of, so u minus v, but in particular, it's larger than the soup at the initial time of u minus v minus whatever is this positive part. Okay, so we would reach a contradiction with the stronger version if we had a contradiction in the weak version. Okay, so that's one thing I wanted to say. So the proof of this, the statement is very long and it looks maybe a bit scary, but the proof is really not very different. You can see in the handwritten notes, it's just a matter of not being afraid and proceeding as before. So no particular mystery in extending the proof we have just seen. And one interesting aspect is that it also, in some sense, in this functional, it tells you how to say this. Like using this result, you can justify, for instance, that if you take two solutions and they coincide on some window at the initial time, then they will still coincide in some cone above this region. So let's say you have two solutions of the same equation, and they are equal at the initial time over a window of space of size, let's say, rho. Okay, so let's say they coincide on a ball of radius rho around the origin at the initial time. Using this result, you can see that they're going to continue to coincide on a cone centered at the origin and of aperture driven by this V guy. Okay, so the V in some sense is giving you a finite speed of propagation type of information. Okay, so maybe yet another way to put it is if you have a solution and you modify the initial condition somewhere very far away, you're not going to notice it for a very long time. Okay. It's not like the heat equation, for instance, which has instantaneous speed of propagation. Are there questions? Okay, so I'm not going to give the proof of this result. If you want to read it, look at the handwritten notes. Maybe as a so let me try to summarize what we have done today. So summary. So we have seen that so let's go back to thinking about our Curie-Weiss model. Okay, so we have these functions fn, and we want to nail down the limit of these functions. So today we have seen that, first of all, the sequence Fn is pre-compact. Okay, this was the easy argument, observing that the initial condition does not depend on n, and these functions are all one Lipschitz, both in T and X. Okay, so by Arzelà-Ascoli, this is true. We have seen that any limit point must be a viscosity solution. And finally, we have just seen that there is a unique viscosity solution to this equation for a given initial condition. Okay, so maybe I could add the initial condition here, which is, okay, we wrote it psi, is this thing which does not depend on n. Fn of 0 dot does not depend on n. And finally, there is a unique solution to this problem. So it's a more abstract way to approach the thing than large deviations, but still we have again achieved the fact that we have nailed down a unique guy, which is the limit of the sequence Fn. Okay, so this justifies fully that Fn converges to the unique viscosity solution to this equation. Okay, is that clear? And so once this is done, we can still wonder about, when we were doing large deviations, we were discovering the limit as a variational formula. And so now we kind of know that, in fact, the viscosity solution to this equation is given by this variational formula, because we have two proofs that identify the limit of Fn, and they give these two identifications. So next time I'm going to discuss this some more. I'm going to explain in what circumstances is it the case that viscosity solutions to certain equations can be written in variational form. Thanks for the feedback. And maybe if I have a few more minutes, then as a little, like today we saw a very complicated theorem about this. I don't know if it's very complicated, but at least the proof was perhaps more substantial than what we had faced so far. Maybe in the last few minutes, I'm going to. Okay, so the question in the chat, the answer to this question is because if you look at psi alpha, if you fix t, if you optimize over t equals t prime and x equals x prime, then this is you're optimizing this u minus v minus chi. Does that make sense? Does that make sense, or would you like me to write it down? Yeah, it makes sense. Okay, cool. Are there other questions? Yeah, so indeed, Luigi is pointing out that we have a social gathering for those who are interested, as last week. I'm going to take a short break, but then I'm going to join the social gathering as well. Yeah, so if there's a few more minutes, maybe I can just play around a little bit and so. Okay, I don't understand the question in the chat. So in the remaining time, I'm going to imagine that we don't know about the variational formula, and okay, maybe it's a bit of a short. Yeah, maybe I don't have enough time. But using the comparison principle, you can learn things about the solution. So maybe I'm not going to do it because the time is short. But it's kind of an interesting thing to do to look at this equation and imagine we don't know about the variational formula and try to infer information about the solution. And for instance, one thing you can do is observe that our function psi, is bounded between, so it's like log of this hyperbolic cosine, and it's non-negative. And this log of hyperbolic cosine, you can bound it by some constant times h squared. So, okay, so 0 as an initial condition will provide for us the solution 0. So using the comparison principle, you know that the solution to this equation is always non-negative. Okay, but that maybe was kind of obvious to us. But you can play around a bit and try to figure out an explicit solution that has the initial condition, which is a parabola. And if you do that, so maybe I was considering explaining this, but maybe I don't have enough time. But I'm just going to splash what is the exact solution. So if you do that, you find that 0 is smaller than f of th is smaller than so ch squared over 1 minus 4ct. Okay, so this I derived using the comparison principle and observing that for t smaller than, so this is for t smaller than 1 over 4c. For t smaller than 1 over 4c, this is a smooth solution to the equation. Okay, so someone understood the question in the chat. Thanks a lot for taking care of this. So you see that you can learn that f will satisfy these two inequalities for t smaller than 1 over 4c just by using the comparison principle. And it's kind of interesting to see that you can learn stuff about your function by just using the comparison principle and some sort of explicit calculations of this sort. So in particular, with this simple calculation, we see that the derivative of f at 0 will exist and be 0 for every t smaller than 1 over 4c. Okay, and then okay, we don't know, and we know that anyway. Ultimately, for t sufficiently large, this function will no longer be differentiable. All right, so that was a bit of an aside for, let's say, for playing around with the comparison principle. Well, thanks a lot for your attention. I'm happy to take more questions if you have. Ah, yes, and as Luigi is pointing out in the chat, in 1.5 hours, if I'm right, then the first mini course by Sarah Pennington is starting.
Yes, so in 90 minutes we start Sarah's course, and Luigi's course is a bit later today. So it will be an hour and a half later than normal for the rest of the week. And the schedule is online, so if anyone is uncertain.
All right, so someone asked whether there's a comparison principle for the spatial derivatives of the Hamilton-Jacobi equation. That's a good question. And I don't know the answer to this question. But it sounds plausible to me. At least in the problem set, I put an exercise which states that if the initial condition is L Lipschitz, let's say, then the solution will be L Lipschitz as well. So okay, let me rephrase it more precisely. So in the problem set number 4, if I'm not mistaken, no, 5, sorry, there is a question of this sort, which you can solve now using the comparison principle. So you take F a viscosity solution to some equation of the sort we have studied. And if this is true at the initial time, then the same bound holds for any time. Yes. So here to solve this question, it's actually not too hard in our context because we are solving the problem on RD. So you can consider translations of the solution, and it's still a solution. Everything is nice. But for instance, for spin glasses, I had to prove something like this, but the domain was more complicated, and so you had to come up with a more refined proof. And in particular, I could only prove it because of so it will depend on the domain in general, for instance, or at least that's my understanding. So I could prove it when this is the little L2 norm for the particular domain I was interested in. But I would really have liked to prove it for another norm, and this I have not succeeded so far. So I don't know if that is true. So let me rephrase the question. So in the spin glass papers, there are functions like this which show up, and they are defined for variables which, okay, let's just say they take values. Yeah, they take values in some cone, let's say. And in this context, I can prove that the same result as displayed here is valid, where everywhere where there is a norm, it's the little L2 norm. And I would really like that it's true also for LP norms, but this I don't know how to prove. So, okay, maybe that's just a display of my ignorance about how to answer your question. It's a good.
Give a hint on how to solve this question. I tried this morning, didn't make progress. Could you just give me some hint how to solve this problem?
Oh, yes, sure.
Homework problem.
You mean the one I'm discussing now? This
just the simple one.
So I'll stop the recording. Maybe I think I can do that.